Bismillahirrahmanirrahim. Assalamu alaikum ji. We will continue our discussion on logistic regression. So far, we had been using logistic regression for binary classification. In this video, we will extend the concept and we will define multi-class logistic regression to handle a case of multi-class classification, or what we call multinomial classification. In multi-class classification, we have our y can take any values from 0 to m minus 1. So in total, we have m classes. We quickly review the two types of classifiers when we discussed multi-class classification previously. We talked about a one versus all classifier and all versus all classifier. To handle multi-class classification or multinomial classification, we defined the building of one versus all or one versus rest binary classifiers. So the idea is we train m different binary logistic regression classifiers h0, h1, hm minus 1. So okay, each of the classifier is classifying zero class with respect to all other classes. H1 classifies one versus all other. H2 classifies class 2 versus all the other classes. So we can say class classifier hi is trained to classify if x belongs to ith class or not. In this way, we have m different binary classifiers. For a new test point z, we obtain scores for each classifier. That is si is a score which is the probability that z belongs to ith class or not. And in this way, since we have m different binary classifiers, we will obtain m different scores. So each score represents the probability that z belongs to that class or not. Once we have these scores, we can predict the label y as a label for which the score we get the maximum score. Right? So we maximize over all the scores and we assign a label which is for which the score is we get the highest score. Right, so that was a one versus all classifier, or we call it one versus rest classifier. We discussed this before in detail. The other option was we use a build all versus all classifier. The idea here is that we construct m choose two different binary logistic regression classifiers. So we want to compare each class with every other class. That's why we need a very large number of classifiers, m choose two. For example, in class we can say classifier hij is trained to classify if x belongs to ith class or jth class. So we have a classifier to compare any two classes out of n classes. Right? For a new test point z, we get the scores for each classifier that quantifies the probability that z in class I or z not in class j. That's how we define logistic regression classifier. We can predict the label y for which the sum of probabilities is maximum. To further explain this, let's take an example. Consider we have a problem in which we have three classes a, b, and c. So we build three classifiers. Classifier 1, that is a binary classifier that classifies a versus b. Classifier 2, b versus c. And classifier 3, which is a versus c. When we get a new test point z, classifier 1 gives us probability whether z belongs to the class a or z belongs to class b. So we get probability of first classifier of having a label a or having a label b. Classifier 2 similarly gives you probability of b and probability of c. So classifier 3 gives us probability of a label being a and probability of a label being c. And we know that probability of 1b would be is equal to 1 minus probability of 1a, right? Because we have a binary classifier. So once we have these probabilities, right, uh, we sum all the probabilities. For example, we sum P1A and P3A. So this gives us the probability that a label can be of a label being of class A. So similarly, you can sum P1B and P2B and P2C and P3C. So we have a sum of probabilities. We select a label for which the sum is maximum, right? For example, if P1B plus P2B is greater than the other two values, we say B as the label for the test point. So we select the label for which the sum is maximum. That is an all versus all classifier. When we defined it earlier, we did not define in the context of logistic regression, but here I think you must have a better idea that what is all versus all classifier and what do you mean by one versus all classifier, right? So in these two options, we have used binary logistic regression classifiers to build multi-class to handle multi-class classification problem. How can we extend logistic regression for a multi-class problem? The idea is we extend logistic regression using softmax instead of logistic. So what was logistic regression? We take a weighted sum of inputs followed by a sigmoid that squishes the value between 0 and 1. Right? For a binary case, we have this case. We have this model, and what was h theta of x, that is probability of y is equal to 1 given x. So this probability represents the probability of membership of class 1. And if I summarize the logistic regression model for binary classification in one sentence, that is a weighted sum of features followed by a sigmoid for squishing the values of weighted sum between 0 and 1. So we will extend this concept and we will build using a similar analogy for multi-class logistic regression. Okay, let's talk about a binary case first. That's how we defined the probabilities for a binary case. H of theta of x, probability of y is equal to 1 given x, 1 minus h of theta of x, probability of y is equal to 0 given x. I can rewrite this using some algebraic manipulation. I multiply by exponent of theta of t of x in the numerator and denominator. I can obtain this probability of y is equal to 1 given x. Similarly, probability of y is equal to 0 given x would be 1 over exponent of theta transpose x plus 1. We know that I can write 1 as exponent of 0. Right? Similarly, I can write these two as this. So I've simply replaced 1 with exponent of 0. Right? Okay, if you observe these two, we have exponent of theta transpose x in the numerator, and in the denominator we have exponent of 0 plus exponent of theta transpose x. This is for when y is equal to 1. For y is equal to 0, we have exponent of 0 in the numerator and the denominator stays same. Right? So we will build on this concept very shortly. Okay, for m classes, we extend the formulation of the logistic function. We again note that the model gives us probability of class membership and we assign the label that is more likely. So noting this, we build a model for mth class for multi-class logistic regression as this. So probability of y is equal to m given x would be exponent of theta m transpose x in the numerator and all other exponent of theta 0 transpose x plus exponent of theta 1 transpose x plus exponent of theta 2 transpose x and so on and so forth for all classes we have in the denominator. So this is simply extension of logistic. In logistic, what we had exponent of theta transpose x divided by exponent of theta transpose x plus exponent of 0. That was probability of y is equal to 1. Probability of y is equal to 0, you simply have exponent of 0 in the numerator. For defining multi-class logistic regression, we have simply extended this here. This is simply an extension. So for mth class, we have exponent of theta m transpose x in the numerator and divided by exponent of theta 1 transpose x, theta 0 transpose x, and so on and so forth. Theta 1, theta 2, and so on and so forth. Right? So we can say a model is a weighted sum of features, and after weighted sum of features, we simply use a softmax function. Right? So this is a softmax function. It is an extension of logistic regression. It is an extension of logistic function. In logistic functions, we only have exponent of 0, exponent of 0 transpose x. Here, instead of 2 exponents, we have m exponents in the denominator, and we only have 1 exponent in the numerator. So softmax is an extension of logistic function. What I have just said, that's how we define logistic function for 2 classes. Softmax for m number of classes would be, you have 1 exponent zm, which is here, divided by sum of exponents in the denominator. This is a softmax for m classes. Right? We can also define softmax when input is a vector. For example, input is say z0, z1, z2. Output would be a vector as well, in which the first entry would be z0 divided by sum of exponents. Second entry, z1 divided by exponent of z1 divided by sum of exponents. Then exponent of z2 divided by sum of exponent, and so on and so forth. This is softmax. Because this is instead of hard thresholding, this is a soft thresholding. I will explain this shortly. Why do we call it softmax? Okay, that's how we have defined a multi-class logistic regression model. Theta m are the model parameters for mth class. A critical assumption here is that we do not have any ordinal relationship between the classes. So we have a linear function for each of the m classes. So we have theta 0 transpose x for 0 class, theta 1 transpose x for first class, theta 2 transpose x for second class, and so on and so forth. We have a separate linear function for each of the m classes. And then we have the softmax function, which takes input a vector of m real numbers, and it gives you m probabilities proportional to the exponentials of the input numbers. Right? Okay, so we have theta m. Since we have d features in the input, for mth class we have theta m0, theta m1, theta md. So we have d plus 1 features for each class. In total we have m classes. We can say that in total we have d plus 1 times m number of parameters. Okay. So we have this model for each class. So for y is equal to 0 given x, we have use theta 0. For y is equal to 1 given x, you use theta 1. Right? You simply use theta 0 transpose x, theta 1 transpose x, and when you pass these linear functions through softmax, softmax simply converts these m numbers into probabilities. So softmax would squish all the values between 0 and 1, and in such a way, when you sum all these values, you get 1. For example, if you sum this numerator for m is equal to 0 to m minus 1, numerator would be equal to denominator, and sum of all probabilities is equal to 1, right? For better understanding, let's see the graphical representation of multi-class logistic regression model. So we have inputs, right? So inputs, so theta 0 is a vector that has d plus 1 weights for class 0. Theta 1 contains d plus 1 weights for class 1, and so on and so forth. Theta m minus 1 contains d plus 1 parameters for m minus 1 class, right? So when x, you take inner product x with theta naught, you get theta naught transpose x, you can theta 1 transpose x, you can theta 2 transpose x, and so on and so forth. You get theta m minus 1 transpose x, right? So we have scalars for each class. Theta naught transpose x is a scalar, right? But each of these scalars, they are in the range from minus infinity to infinity. So if you want to see where is a binary case here, so binary case, you only have one theta, right? So binary case, if we want to draw a binary case here, that is simply this. This is the binary case. You only compute one theta naught transpose x, and you pass through a sig. Instead of softmax, we have sigmoid, right? And why did we use sigmoid? To squish the values which were from minus infinity to infinity, so that after sigmoid you get the values between 0 and 1. You get probability measure. Here the softmax is doing the same thing. Softmax, in the numerator we have an exponent, in the denominator we have a sum of exponents. So it will always give you value between, so this would be between 0 and 1 closed interval, right? So softmax takes m inputs, m scalars, which are from minus infinity to infinity, or you can just say a vector of m values where each value can be a real number, and output of softmax has m values, and each value is between 0 and 1, and when you sum all these probabilities, you get 1 by definition. And once you have this multi-class logistic regression model, how do you carry out prediction? So we compute h theta 0x, h theta 1x, h theta 2x, and so on and so forth. We have m probabilities. We assign the label for which we simply assign the most likely label, or the label for which h theta m is maximized. I hope this is clear. So before we conclude, we can also formulate the cost function or the loss function for multi-class logistic regression. So for binary classification, we had this loss function. If I ask you to pause a video and try to extend this for multi-class logistic regression case. Okay, I give you a hint. What are we doing here? We are computing the sum of sum of probability, log of probabilities, right? So log of h theta of xi. So this is the h of theta of xi is the probability of when yi is equal to 1. And similarly, 1 minus h of theta of xi is the probability of yi is equal to 0. Right? So when actual label is 1, you use log of h of theta of xi. When actual label is 0, you simply use log, which means you take a log of 1 minus h theta of xi. We are simply computing the log of probabilities of each yi, and we're simply weighting by yi. So this sum would be equal to the number of points in your training data for which yi is equal to 1 times log of h of theta of xi plus the other is number of instances times log of 1 minus h theta of xi for each of xi. If you extend this for multi-class logistic regression case, this is what we get. So here, a log of h of theta m xi. What is this? Probability y is equal to m given given xi. We simply take, so this is this term. We take a log of that, right? And this is delta function here, right? So this delta function gives you 1 when the true label is m. Right? So probability of y is equal to m will be counted only when for xi the actual label is 1. You have a match, right? And we simply sum over all classes and simply sum over all instances. Right? And if I use the mathematical model we developed for h theta m xi, here I can get this loss function. So we won't spend time on minimizing, on finding the gradient of this, but if you know that, so for sure, this loss function is a convex function of theta, and we can use gradient descent to find d plus 1 times m number of parameters of the multi-class logistic regression model, right? So that was a quick overview of multi-class logistic regression. How can we extend? How can we extend a binary classification? How can we use logistic regression for binary classification for the case of multi-class logistic regression? If I summarize logistic regression, in both binary classification and multi-class classification, so they use regression followed by mapping to probability space using logistic function for binary case, and we use softmax function for multinomial case and multi-class case. So when we used my apologies, in logistic regression we did not make any assumptions about distribution of classes in feature space. We saw that decision boundaries separating classes are linear. We saw for a binary classification problem, and the same is true for a multi-class classification problem. And we also saw how can we tweak, how can we manipulate the features to obtain non-linear boundaries. Logistic regression provides a natural probabilistic view of class predictions because for each class we are getting probabilities of having a test point in that class. We formulated loss function using the cross entropy loss, that is a natural measure to compare or to evaluate or to define loss when we have output of a classifier expressed in terms of probability. This model can be trained very quickly using gradient descent, and once the model is trained, it can be the prediction or classification is very computationally efficient, because to carry out prediction, to carry out classification, we simply need to compute the inner product between model parameters and input, and you pass this inner product through sigmoid and you get probability. Or finally, we note that the model coefficients can be interpreted as indicators of importance of the features. So parameters in logistic regression also gives you an indirect measure or indication about the importance of the features, or the contribution of the features or significance of the features towards the final probability or the final classification, right? We stop here, so that's end of logistic regression, and we'll continue in the next video inshallah. Allah Hafiz ji.